Discover the secrets of a civilization in this video.
The ancient Near East was a geologically violent place. Routine earthquakes tore through traditional mud brick cities, reducing massive settlements to rubble in seconds. But as the dust cleared from these violent tremors, one colossal stone palace complex stood entirely unharmed. The columns didn't snap. They were built to sway and wiggle, absorbing the shock before settling back into place. The year is 515 BC, and you are stepping onto the ceremonial jewel of the Achaemenid Empire, Persepolis. When you look up at these massive stone bowls with human faces, the lamassu, you see the physical manifestation of an empire spanning 3 continents. To build this capital, Persian royal engineers chose a rugged mountain slope sitting directly on an active fault line, and they did this thousands of years before the invention of modern cranes, rebar, or rigid concrete. So how exactly did the world's first superpower achieve structural, earthquake-proof miracles that modern engineers still struggle to replicate today? Look at the sheer scale in this photograph. Darius the Great wanted his imperial center right here at the foot of Mount Ramet. It was a jagged mountain slope, uneven and unsuitable for supporting heavy stone monuments. Instead of finding flatter ground, thousands of stonemasons spent years cutting away millions of tons of solid limestone to reshape the mountain itself. They filled the deep natural valleys with colossal stone blocks, some weighing over 88,000 pounds, creating a massive elevated platform spanning nearly 1.5 million square feet. This diagram illustrates how they built the retaining walls to hold that terrace up with zero mortar, mud, or cement. They used a technique called anastylosis. They carved the giant stones into irregular, interlocking geometric shapes that fit together so perfectly you could not slide a piece of paper between them. By avoiding straight horizontal seams, they ensured the wall behaved differently under pressure. When the earth shifted, the interlocking blocks moved together as a single fluid wave of stone, absorbing the geological stress instead of rigidly resisting it. By rejecting rigid cements, the engineers turned the mountain's natural instability into a structural asset. This fluid foundation survived millennia of soil erosion and shifts without ever collapsing. But a shifting foundation won't protect towering vertical columns from the raw kinetic energy of a direct earthquake. For that, the Achaemenids had to invent a primitive, highly effective shock absorption system. Here is exactly how they stacked the massive stone drums of their pillars. First, architects carved matching dovetail-shaped grooves into the top and bottom of adjoining stones, dropping in a heavy forged iron bar to lock them horizontally. Next, workers poured molten liquid lead directly into the groove, completely encasing the iron bar and cooling into a solid seal. This served 2 vital functions. First, the lead completely sealed the iron from oxygen and moisture. This prevented the iron from rusting, expanding, and cracking the stone from the inside out. Second, lead is a soft, malleable metal. When a powerful earthquake hit, the stone blocks microscopically slid and vibrated against each other. The lead acted as a flexible cushion, absorbing the energy of the seismic waves. Modern rigid concrete often snaps under heavy seismic tension. The Persian palaces survived by intentionally wiggling, swaying, and settling back into their original positions unharmed. This image captures the vertical ambition of the Achaemenids. These limestone pillars soared over 65 feet into the air, the height of a modern 6-story building. Reaching that height required a specialized understanding of structural physics. And as you can see from the scale of these trees, the columns weren't standing empty. They had to support sprawling, heavy wooden roofs made from imported giant Lebanese cedars. As this surviving piece shows, they placed multi-ton stone blocks carved into twin kneeling beasts at the very top of each column. These zoomorphic capitals served as perfect cradles for the heavy, sprawling roof beams. This cross-section demonstrates the mechanics at play. By splitting the beam's weight evenly between the backs of the 2 animals, the architects perfectly distributed the downward structural stress straight down the center axis of the column. This prevented any uneven loading that would cause the tall pillars to buckle. To hide the horizontal seams where the huge stone drums were stacked, builders carved up to 48 delicate vertical flutes, or grooves, into the shafts. This manipulated light and shadow, making the heavy columns look straight and forged from a single, unbroken piece of stone. These column forests were highly calculated mathematical solutions designed specifically to manage the relentless downward force of gravity. This carving of the seated king represents the political reach of the Achaemenid Empire, but beneath the surface of the palace, the engineering reveals how deeply they understood the physics of their environment. These structures have stood for 25 centuries because the Persians didn't try to fight the earth with rigid strength. They engineered a way to move with it. They conquered the solid rock and the shaking earth. But how did they handle the invisible elements? How did a palace complex in the desert survive sudden flash floods and devastating droughts? To answer that, we have to look underground, plunging down into a hidden labyrinth of ancient water tunnels and exploring the prefabricated building techniques that allowed them to assemble entire cities in a matter of months. Hit the subscribe button and join us for part 2 as we descend into the dark hydraulic secrets of the Persian masters. In part 1, we examined the towering limestone columns of Persepolis. But to understand how these palaces survived, we must look past the surface architecture and go straight down into the dark, silent bedrock below. Persepolis sits on the Marv-Dasht Plain, a landscape defined by extreme weather. It spends most of the year as a dry desert. Then winter hits. Violent, sudden downpours crash down the slopes of Mount Rakhmet, unleashing massive walls of water directly onto the artificial terrace. In the ancient world, standing water was a death sentence for a building. If those flash floods sat on the platform for even a single day, the water would seep into the foundations, rotting the timber beams and turning the soil to mud until the multi-ton columns tilted and collapsed. To keep their capital from dissolving into the earth, the Persian builders had to outmaneuver the environment. They designed a defense system that neutralized these sudden floods the exact moment the rain hit the stones. Years before the first palace brick was laid, laborers tunneled directly into the solid rock foundation of the terrace. They excavated a sprawling, miles-long network of subterranean drainage canals. Forget shallow gutters. These tunnels were carved over 6.5 feet high and almost 5 feet wide. They were large enough for a grown man to walk through the entire maze completely upright. This cross-section demonstrates exactly how the system worked. Every courtyard, hall, and roof gutter featured hidden vertical drain holes carved out of solid stone. When a storm hit, the water didn't pool on the surface. It plunged straight down these vertical shafts. Once underground, natural gravity took over. The micro-calculated slope whipped the water away from the foundations, safely out through the retaining walls into the fields below. The Achaemenids built an invisible hydraulic machine. They took a chaotic, destructive force of nature and channeled it into a controlled, highly predictable water delivery system. Protecting a single city from floods is one thing, but Persian kings built massive administrative centers like Susa, Ecbatana, and Persepolis across thousands of miles. Accomplishing that in a short period of time required an entirely different type of engineering, logistics. This map displays the connective tissue of the empire, the Royal Road. Built by Darius the Great, it was a highly engineered highway stretching 2,700 kilometers from modern-day Turkey to Iran. It featured packed gravel, paved stone bridges, and exactly 111 post stations spaced 1 day's ride apart. This high-speed grid allowed the empire to centralize its architecture. Instead of quarrying everything on site, off-site stonemasons worked in specialized workshops kilometers away. A central royal architectural bureau dictated uniform measurements, and the masons carved blocks, column drums, and door frames to match perfectly. To keep track of it all, each workshop stamped its finished stone piece with their unique signature. If you look closely at the base of the columns or the hidden joints, you will find these tiny carved geometric symbols, like tridents, circles, and stars, indicating exactly where each piece belonged. When the pieces finally arrived at construction sites like Persepolis, the crews didn't waste time cutting or measuring. They simply read the marks, lifted the blocks into place, and locked them together like a massive 3D jigsaw puzzle. The Persians successfully executed mass-scale standardization and modular construction centuries before the modern world adopted those same techniques. They turned empire building into a high-speed assembly line. When you look at the Tachara, the private palace of Darius the Great, the black limestone doorframes stand out from the rest of the site. They are so smooth and dark that they reflect the surrounding mountains and sky like glass. Achieving this finish, known as a mirror polish, required intense manual labor. Artisans shaped the raw stone with iron chisels, then rubbed away the scratch marks with coarse sand and powdered pumice. Finally, they buffed the limestone with oil-soaked leather cloths for months on end. This extreme attention to detail served a highly practical purpose. The glass-like polish compressed the surface until the stone became entirely non-porous. It created a waterproof seal that prevented any moisture from entering the royal doorways. These microscopic details were highly engineered defenses. The builders applied an invisible layer of armor to ensure the structure would survive the slow, relentless weathering of the elements. In 330 BC, Alexander the Great's army swept through Persepolis. They torched the giant Lebanese cedar roofs and melted down the gold and silver tapestries until the city was entirely consumed by flames. The conquerors left the capital in ashes. By destroying the visible architecture, they assumed they had permanently erased the Persian superpower from history. But the fire couldn't melt the 135,000 square meter bedrock terrace. It couldn't shatter the mortarless, interlocking stone blocks, and it couldn't bring down the massive megaliths built to withstand earthquakes. Even more remarkably, the hidden underground water labyrinth survived intact. Today, 2.5 millennia after the empire fell, those same hand-carved tunnels still function perfectly, swallowing violent winter floods without hesitation. The Achaemenids designed their empire to endure. Through meticulous standardization, subterranean water management, and weather-proofed stones, they mastered the forces of nature, leaving behind an architectural footprint that outlasted the flames of war and the centuries of time.